Hello, my name is Simona, and in this video I'm going to present a final project work done for the course Network Softwarization Technologies and Enablers with my partner Pridika on the topic Fog-enabled object detection using multi-tiered cloud platform Savvy. I'm going to give a definition of fog computing, and then I'm going to mainly focus on four things: showing an application that does video processing and counts number of vehicles, and describing the cloud platform which is used and our contribution towards enabling fog computing, then describing two fog computing implementations, communication messaging protocols between the cloud computing and the fog computing devices, and the installation of the video processing application using the method of containerization. And the last part, I'll do some performance analysis for the communication protocols and the containerization depending on the processing resources. First of all, fog computing represents a distributed computing paradigm that acts as an intermediate layer in between cloud data centers and IoT devices and sensors. It offers compute, networking, and storage facilities so that cloud-based services can be extended closer to the IoT devices and sensors. Moving on forward, I'm going to show an application that has the end goal of vehicle detection and counting. Since image processing has been a hot topic in recent years, and vehicle detection, tracking, classification, and counting are very important for applications such as highway monitoring and traffic planning. This application is going to process images obtained from video sequence and detect moving vehicles. It has four parts, as can be seen here, and the walkthrough is the following. We capture a video stream from a web camera. Then, once the system gets the video feed, it will start transforming it and sending it frame by frame. And every frame will be processed to find a moving object in the video. To do so, first we get the foreground from the images by subtracting the background. And then, since this traffic and vehicle lights can highly influence on the detection and consequently on the counting, we'll save the number of frames and try to assess which of the pixels are the same for most of them. And those pixels will become part of the background layer. And we're using 500 frames to do background subtraction, and the rest, which is part of the training sequence, and then the rest of them are used for the testing sequence. And this part of the algorithm is actually referred as filtering. And after subtracting the background using filters to cope with different influences of the implementation, we will use the C++ open source library, OpenCV, and the method find contours, which is going to detect all the contours on the frames and give us the output. Then from that output we can implement some filters in terms of parameters, geometry and stuff like that to filter out all the other objects from the frames which are moving but are not vehicles. We can go to the VM in the cloud platform, and we can actually see the vehicle counting code. And what we're going to do now to show the outline of the code, we're going to run this code and observe what it's going to do. So in the first part, it's training, and it's using the first, as I mentioned, 500 frames, and then we'll do the process as explained. We also have a Node.js server running on this VM, so we can display some of the statistics, such as the number of vehicles depending on the time, and also the processed video. By doing to do so, we need a CSV file which contains time and number of vehicles, which is here. To kind of visualize that, we're going to go to the browser and put the address of the VM, the port on which the server is running, and then we go to index.html. So here we can see the vehicle arrival rate, so number of vehicles as a function of time. And then here we can see the processed video. So we have the detection. You can see the red squares, which are detecting number of cars, and then we have exit zones on both sides of the road, whose job is to actually count the number of cars. So this is how our application is developed. And then the second part, which was mentioned earlier, is proposing separate implementations of the camera feed analysis and integration with a cloud platform, which in our case is called Smart Applications and Virtual Infrastructure. So we go here, we can see that first of all, the Savi project is envisioned as a cloud platform that has 3-tier architecture. Tier 1 has core data centers that are traditional data centers. Then Tier 2 has smart edges that are agile data centers residing close to end users, but also providing other heterogeneous resources, such as software-defined radio, programmable hardware, GPUs, wireless access points, and so forth. And this smart edge is mainly used to deliver quality applications that require high responsiveness and have requirements that can only be satisfied with a heterogeneous data center closer to the end users. And the smart edges are connected to the core data centers through backbone networks. And finally, Tier 3 has sensors. And in the Savi nomenclature, this is called an extended edge, which kind of extends cloud management and functionalities to the customer's premise to support various demands from the customers. The extended edge kind of represents a genuine extension of the Savi Smart Edge. We need to have a small set of virtualized resources that can adaptively program to be able to deploy a certain application. And the reason behind this deployment is the fact that we can easily control their life cycles, reprogram, delete, redeploy, etc. So the first implementation involves Raspberry Pi as an extended edge. Raspberry Pi represents a very lightweight and expensive node, which can be mainly used to provide connectivity to a cloud environment. It has a ARM-based development kit, very small in size, uses SD card for storage, has onboard memory, and can be used as a supportive device, which has a task to receive the camera feed using a Docker container and send images to a Docker container in the VM running in Savi. So what is Docker? Docker is a tool designed to make it easier to create, deploy, and run applications by using containers. And containers kind of allow the developer to package up an application with all of the parts it needs, libraries, dependencies, and ship it all out as one package. And this brings a sense of certainty that the application will run on any Linux machine regardless of any customized services that the machine might have. And Docker also allows applications to use the same Linux kernel as the system they're running on, and so it gives kind of significant performance boost, reduces the size of the application. We can go to the Raspberry Pi here, and by running this sudo docker ps, we will list all the running containers. In order to see in order to attach to the Docker container, we can run this command, which is going to give the name of the container. And as you can see now, we're in the container, and we go here. We're going to see in this folder test, we're going to find a lot of frames being sampled, and this folder pub has the publisher, which is going to be used to communicate with the Savi VM. So now we'll focus more on the networking part, and if we do ifconfig here, we're going to see that there are a lot of interfaces, but mainly we're going to focus on a few of them. we have enabled, as you can see here, and this is quite an important part, we have enabled two types of communication. And the first one is enabling multi-host overlay networking with Open vSwitch. And so to do this, we have installed Open vSwitch on both sides of the communication, and we have established a general routing encapsulation tunnel between them to give some kind of network virtualization sense to this project. And so if we want to see, for example, the bridge that is used to deploy this network virtualization, we're going to run this command. Another thing to notice here is that actually we're using GRE as a communication protocol to establish a direct point-to-point connection between network nodes. And why? Because it's simple and effective method of transporting data over a public network, such as the internet, but in a secure way. And the communication is between the containers running in the Pi and the VM, which is trickier than only establishing GRE tunneling between VMs, which is making this more exciting. Then what we can notice next is, besides this communication, we have also enabled communication between the containers running in the Pi and the VM using MQTT, which is a well-known messaging protocol. And MQTT enables IoT devices to send, publish information about a given topic to a server that functions as an MQTT message broker. And this broker here, we're using Mosquitto messaging broker, is located in a virtual machine in Savi. And this broker pushes the information out of the clients that have previously subscribed to the client's topic. So if we go to the virtual machine in Savi, which is actually if we go to the virtual machine in Savi, which is actually our subscriber, and we go to this subdirectory and we run the subscriber here, it's going to ask about basic information about the broker, such as the IP address, the port and which one is listening to, and similar stuff. And then what we'll have to do next is go to the Raspberry Pi, and again here we have the publisher and we have the images that need to be published. So we're going to run the code, and we're not surprised that it's asking for the same information, such as the Mosquitto IP address, the port, the topic, and when to publish from. So we can see that we have 56 images to publish, and we can see on the Savi VM that those are being published. And this messaging protocol will work in a way that the subscriber will continue waiting, and the publisher will publish as soon as it gets new information in the same directory. And then the next implementation of an extended edge is Linux Bricks. Linux Bricks is on a Linux PC which comes with an Intel CPU, supports 8 GB of RAM, and it's relatively compact in physical size, which allows it to be located in any convenient location. And the Linux Bricks has the possibility to host numerous Docker containers which we select from the environment for the application in order to make the deployment very modular and easy to control and modify. And this crucial point in the installation of bricks as the extended edge is that it can offer almost the same functionality as the VM in Savvy. And for a chosen use case, the bricks can run the application to count the number of vehicles and accordingly publish the information. And moreover, it can create a video which shows the counting of the vehicles. And this process can consume quite a good portion of the resources. And this means that the bricks can adapt to an environment needs, in a sense that if only one application is running, then the bricks can act as an edge computing device and not even require sending the video feed for analysis in Savvy. But however, it is possible that we have more applications running in the same device. And this has become easier since containerization with Docker has become reality. And if that's the case and we need more applications running on the Linux bricks, then we can send the images to the VM in Savvy using the MQTT protocol for further processing, thus having a fog computing role. If we go to the bricks, what we can notice here is basically we can do ifconfig and see all of the interfaces. Again, we can notice that the same implementation of the communication is used. So we have the GRE tunnel, we have all the interfaces that are being previously used. We have and stuff like that. So what can be shown next is listing the Docker containers in the VM. So we can see that we have one container here, and in order to see the outline in the container, we can run this command, and as we can see now we're attached to the container. If we go to the home directory, you can see here that we have put all of the information, the vehicle counting application and stuff like that that can be used to deploy the application. And what we're going to do next is throw in some kind of analysis. If we go on this IP and port, but instead use statistics.html, we can see two statistics, and I'll elaborate more on both of them. Since we need near real-time analysis and of the implementation, we will try to analyze the end-to-end delay in the two implementations, and we'll pay attention to different messaging protocols and the delay that they induce. And later we'll make an effort to quantitatively evaluate the latency of the application. So as mentioned before, we have used both MQTT and the GRE tunneling, and the way to use the GRE tunneling to send frames is using the HTTP post method. So we have HTTP and MQTT communication with the between the containers in the fog extended edge and the VM in Savvy. And well, we tested the performance of these methods by sending frames from the extended edge to the Savvy VM and notifying the delay. It becomes intuitive that a publish-subscribe concept is more suitable, and as the statistics show, this is the reality, as we can see that the second option, the MQTT messaging protocol, handles message as soon as it's received, and it's making this very efficient and reliable. And the results show that the time needed to send an image grows exponentially when we're using HTTP, and in contrast, MQTT is showing almost linear dependencies. So we can see here we're sending one image and they can also comply at the same time, but when we send 25 images, HTTP uses almost the same amount of seconds to send 25 images, whereas MQTT only needs like 4 to 5 seconds to send 25 images, which is quite good. Now another statistic is the performance of the two Docker containers running in the same vehicle counting application. So one in the Linux bricks and the other in the Savvy VM. Usually Docker takes care of the amount of resources it gives to a specific container, which can be tracked running a simple command docker stats and the container ID. And the default behavior is that a container has no resource constraints and can use as much of a given resource as a host kernel scheduler allows. So since we're not putting any upper boundary on the amount of resources that Docker might assign to a specific container, we can say that intuitively the VM will outperform the Linux bricks as the number of minutes for a video increases. And we can notice that on the second graph as well. So on the x-axis we have the number of minutes that a video length is, and on the y-axis we have the time needed in seconds to process the video. We can see here that the Savvy VM complies much better as the number of minutes increases, whereas the Linux bricks, it becomes impossible to work even near real time as the number of minutes increases for more than 15. So this is due to the fact that Docker in the VM has more resources, and this application is computationally exhaustive, and the resources in the bricks are starting to be insufficient for the application to work in real time. It cannot cope with the speed needed. So this is basically everything that we needed to show in this video. So in this project we tried to encompass a full deployment of an application that requires somewhat heavy processing, the whole data pipeline from the web camera that gives us the video feed to getting frame by frame into a extended edge of Savvy, and then sending those frames from a container in the extended edge to a container in the Savvy virtual machine. And the accent was given on both a timely, accurate execution of the application, finding an appropriate messaging protocol to safely transmit data, but also time effective. And we discussed two network deployments in the three-tiered architecture of the Savvy testbed, how extended edge should be designed and implemented as a third tier in the architecture. And we did try to focus on implementing technologies and using tools that were taught throughout this course. So thank you.